So we had continued up to the point of making these equations, creating these equations. So as you notice that it's just the matter of knowing the pressure distribution diagram, and the force is the area of the pressure distribution diagram, and these pressure diagrams they are either triangular or rectangular, and you know the centers of the shape. So if you take moments probably at the bottom, then it's easy, you can create. So this is the more complex of the versions of the equations, which is not required, but you can see, you just see is presented here for you to see the accuracy with which you can solve. Now if you use the simplified version, then you only need this, and the simplified version is here. The simplified version is you have only three. This is on the passive side, on the active, and this is the contribution from the surcharge, and then you only make three equations. Each of them can, if you take the moment at the bottom, then one, if the you consider one of them positive, so the probably the clockwise, I should say, is positive, and these others are negative. So three equations and with only one factor d naught, which you can guess and check, or if you have a good calculator you can solve. It comes to about 6.98, and you have to increase by a factor of 1.2, because remember we are ignoring this that makes it easy to solve, but we are ignoring the fact that point OB, we are ignoring OB in figure C. So for that reason, once you solve, you have to multiply by a factor of 1.2, as shown here. You can see it's a little bit overestimated, but that's okay. So for the CP2 method, the only difference is how to determine Ka. Not okay. Let's go through so that it's clear as well. So for in the CP2 method, the net passive resistance below the point of rotation is reduced by the horizontal R, as shown in figure 6. So this is the representation for the CP2, but you can see that we are assuming some passive some point load for the R, for the passive resistance. So please note that difference, and also note here that we are reducing the passive resistance by half based on this if you read it through here, yes, here with it is in practice to divide the theoretical value by 2, okay, by a factor of safety of 2. So that factor only applies for the passive side, okay, and also we reduce that passive force by concentrated load. So that's the idea. So please note this difference. So this is the force distribution on the passive side, but typically this is Kp times gamma times d naught, but we're supposed to reduce it by half according to the gross pressure method. So this is A. Down here we have K gamma plus 5 d naught, so that's okay, but we have to reduce that force by a point load, the passive. So this, you can see these are functions to reduce because the resultant direction of the passive force is this way. So the passive force is reduced by R. Okay, so that's a point. So using Rankin's theory, and for this method the phi is the same. Phi is still 30. So you can check in your calculators. Please make sure you can check that in your calculator. So phi peak is still 30 for the CP2 method. So in that case, then phi is 30 degrees, A is a third, you can check, and Kp is 3.0. Now this one actually is very simple, because in fact you can ignore this R that we reduce on the, if you are taking moment, it's just at the bottom, so this R has no moment at the bottom, so you are very lucky. Having said that, if you take moments at the bottom, this would be the area of this is a half times this times d naught over 3. So okay, let me write here, maybe it will help someone to understand. So the moment at the bottom, so we take the moment at the bottom there, the moment because of this would be half times half, because is already, this half is because we already have 0.5 there, so times Kp times gamma times d naught, but d naught squared, because d naught times d naught over 3. So it should be very easy. So this is 4 times 3 is 12. I don't know, 12. Let's see what they get here. So 15d squared, you can see that that is true. No, that's not true. So this is 4 times 12. For the passive side, how come is 15? Sorry, you guys, why are you not, people? This is 5, right? This is 3. So let's see. So for the passive side, we have a half times Kp. Kp is 3 times times 20. I think it's 20, I believe, times d naught over 3 over 3. Of course, this is times a half again, because it is customary to reduce. This half is already this one. So this one, 2 times 2 goes here 5 times. So you can see where the 15d squared comes from. So you can see here, and I need some response. People are just quiet, even if there is some mistake. Are you seeing? So this, you can see why we are getting 15d, 5d cubed in fact there. So this is not right here actually. So you can see here, if you multiply, actually this one divides that, so then actually you just end up with 5. actually d cubed, so one of this is d squared, d naught cubed. Please confirm that you can see how we are getting that solution. Hello?
Hello, sir. We are following, sir.
So you can see how we get 5d cubed.
Yes, sir.
Okay. So it should be very easy actually. This is a half. Okay, I'll try to repeat again. So the formula itself, this one is already a half times kp is 3 times 20 times d naught. Okay. So this is what is written here, but the formula is a half times base. So this is the base times height d naught. So that is the force times the lever arm, which is d over 3. Okay. So this is 4, 2 goes here 10 times, 2 still goes there 5 times, and this is, there you can see that is 5 d naught cubed, and this is what you can see here. Okay, so that, I think that should be simple. The same idea on this side, the same idea on this side, so that would be a half times ka. So I think we need to substitute the actual value. So Ka is a third, so that would be a half times the third times 20 into 5 plus d naught. So that is the half base times height. So 5 plus d naught. Of course, so that's the force. So times 5 plus d naught over 3, and you can simplify that. So that's what you see here. Sorry, that's the what you see there, and I'm sure you can simplify to this. So you can say, because you can say that the passive moment over the active moment, the A, should at least be 1. So then you say 5d, you can see 5d cubed over, and then you can guess and check which value gives you 1. You can see this is this overestimates the d naught a little bit. We have 7.7 and then d is 9.24. So you can see so this one gives you maybe the highest value, and this one maybe is a little closer. The first method, the ABS8002 method, gives you a value that is probably closest to this one's. Alright, so you can make your own judgment as an engineer out there in the field. So that's the point. So unless there's a question for this part, so you can guess and check. Maybe the difficult part there could be from the mathematics, but that I think that should be the easiest part. How to solve. Okay, so the anchored propped walls, when the top of a sheet pile wall is anchored, a considerable reduction in penetration depth can be obtained. So when you anchor the top of the sheet pile wall, Due to this anchorage, the lateral yield in the upper part of the wall is similar to the yield in the timbered trench, whereas in the lower part the yield is similar to that of retaining wall yielding by rotation. So if you anchor the top part, shown here, if this is has some anchor, then you can substantially reduce uh, the penetration depth. So as a result, the pressure distribution of the back of the anchored sheet pile is a combination of totally active and arching active cases, the probable pressure distribution being indicated in figure 7b. So it's the anchoring, while it reduces the depth of penetration, the distribution of pressure is quite complicated. You can see here we are saying probable. That means it's an estimation. It's difficult to get the pressure distribution precisely. So in practice, the pressure distribution behind the wall is assumed to be totally active. The anchor or prop force required can be obtained by equating horizontal forces T, which equals PA minus PP. So if everything here has to be okay, from which a value is obtained per meter run of the wall, the resulting value of T is increased by 25% to allow for flexibility in piling and arching in the soil. Anchors are usually spaced at 2 to 3 meters. So, yeah, because of this, we say everything here. All these forces have to be balanced. So, how to get PP is so assume T is positive. Assume T this direction is positive. That means forces in this direction are negative. So if that is the case, then we say T positive T uh, plus PP minus PA. It should be 0. In other words, we can say if we want T to be the subject of the formula, we can say then negative T is PP minus PA, and therefore T is PA minus PP. So PA is usually larger. PA is usually larger, so that only means that the tension direction is the other side. So this is just based on your assumption. So based on the summation of horizontal forces equals 0, then you can get the tension, the anchor force, which is not difficult. In fact, you know all this. So the challenge would be, you can see the distribution of the pressure there is quite complicated. Uh, so there's a simpler. Let's see the way we can. So once you do that, T is PA minus PP, of course, and then we can say you can increase the tension, the T, not the tension, sorry, the anchor force by 25% to allow for the fact that the sheet pile wall is flexible, and the arching or in the soil. So anchors are spaced between 2 to 3. Arching is this idea observed in sand. I think I've said it in this class. Arching is we know in theory that the in theory we know that the pressure distribution here is, so this is the vertical force we are talking about, so gamma times Z. And so in theory it means if you have an infinite depth, then this curve will continue in a straight line there. However, in reality, in sand, especially dense sand, you realize that there is linear variation, but up to some critical depth. After some critical depth, the pressure remains the same. So gamma. So this is the critical depth. Let's say critical ZC. So up to a critical depth, then this is the actuality. So this is due to arching of the soil. That's the idea, and this is observed in dense sand. Is observed in dense sand. So once you estimate once you calculate the anchor forces due to the arching and also flexibility, you increase that force by 25%. So the anchors are remember there is a length in this direction. Don't forget that there is a this is y, this is x. There's a length in the z direction. There's a length. So this is what we are saying. So this anchor. So if you are to take the z direction, this is the length. So that means you can put an anchor here, an anchor there, an anchor there, and this distance are 2 to 3 meters. So between 2 to 3 meters. That's what we are saying, 2 to 3 meters, because the force we are calculating here is per unit meter, per unit meter run. You can see here per unit meter run of the wall. So you have to consider the actual length of the wall in the direction perpendicular to your eyes. So anchorage can be obtained by use of additional piling or by anchor blocks, large concrete blocks in which the tie is embedded. Any anchorage block must be outside the possible failure plane, and when space is limited, piling becomes necessary. If bending is to be provided in the anchorage pile, then a pair of raking piles can be used in Figure 8C. So we are saying, so this is the possible failure zones of the anchor mass. So you remember the idea of the geotextile as well, geotextile design as well. So we said here, we said this is your wall, this is the potential failure zone. So the geotextiles have to be designed such that the length is outside the geotextile. So this one was used a lot on thicker rod. So the length of this is what we call embedment length, must be outside the potential slip or failure zone. So this is the same idea with the anchor as well. So this is the anchorage. So again, if you anticipate some moments also, then you provide some support, some, what is they call, there's some rake, what is it, pair of raking piles as shown in C, and when this is limited, so when we don't have, because you can see here, to extend this beyond the slip zone, we need some space. So when space is limited, you can do this, but you can see now this is still anchored beyond the. So this is what you can do. If you have a potential, these piles they have to, not the piles, there are moments. Then you provide the breaking piles as shown. Okay, so then we talk about free earth support method. It is assumed that the rotation occurs about the anchor point and the sufficient yielding occurs for the development of active and passive pressures. The pressure distribution assumed in design is shown in figure 7. Figures in figure 7. So this is the assumption. The wall being considered free to rotate about its base, point B. So the wall is assumed to be able to rotate uh, at point B. By taking moments about the tie rod at D, taking moments at D, uh, an expression for penetration depth D can be obtained. The actual penetration depth being taken as equal to 1.2 D. The four methods of assessing the ratio of the restoring moments due to overturning moments described for cantilever walls are also used for anchored piles as well. So the same idea, actually, free earth support. You assume the pile is rotating from here. Then you take moments about point D. The beauty is if you take moments about point D, then T will have no moments, and will simplify your work. Of course, the depth of penetration you get has to be uh, uh, multiplied by a value, has to be increased by a value of 20%, or you the D you determine from there. The D naught you have to multiply by 1.2 as we have done before. Then we have, that's free earth method. There is fixed earth method. The pressure distribution assumed for design work is shown in figure 9. That's the so with a point of contraflexure introduced by the assumption of fixity, the wall can therefore be regarded as two walls, AO and OB. So the wall can be considered at AO and OB. Point of contraflexure means that the wall can do this, or so this is a point that that is the point of contraflexure there, or we can, or the wall can do this. Sorry, here. That is the point of that is what contraflexion means. So entirely separate from each other. This form of analysis being called equivalent beam method. Analysis by elastic line method Trezagi gives the following positions for O depending upon the value of phi for the soil, where h is the height of the wall and x is the dimension shown in figure 9a. Based on different assumptions, you can have varying values, different values of x from point O. Sorry, I just realized that the point of contraflexion is not is there, sorry, or here, or that's the point because that's where the pile can rotate. So based on different values of phi, that value x is different. So you can see when the phi is increasing, the x is getting smaller and smaller. With a high phi, x is bigger. Okay, so these are based on different values of phi. The you can see the various values of the position of x. For most backfills, the average value of phi is 30 degrees. This is not right. Hence, if x is assumed equal to 0.1, a little error will be generally involved. So, because of the complexities, we like simpler ways of being able to estimate these values. And so you can see the table for the x, the position of x um, based on values of phi. And if we know that embankments are usually have embankment material is have a friction angle of around 30, and that even makes the this very this simple, because you can just make an assumption on the position of the position of the x, or of the point of contraflexion. So we can assume, so when the angle of friction is 30, we can assume that x is 0.1 h. So with some error, the actual value is 0.08. So, but we like the round figure. You can 0.08 is a little odd, so zero point 0.1 is seems neat. So the error introduced would be generally little. Of course, the main aim is to make sure we have a safe design. So either way, you still have a safe design. So reduction design moments of design moments in anchored sheet pile walls. Now, this guy called Rowe in 1952 conducted a series of model tests in which he showed that the bending moments that actually occur in an anchored sheet pile wall are less than the values computed by the free earth support. This difference in values is due to mainly due to arching effects within the soil, which create passive pressure distribution in front of the wall. This is considerably different from the theoretical triangular distribution assumed. You see what I'm saying? For the analysis, because of this phenomenon, the point of application of passive resistive force occurs at much shallower depth than generally assumed value of d over 3, where d is the depth of penetration. Roll later extended his work to cover clay soils 1957 and 1958 and suggested a semi-empirical approach covering the main soil types where by the value. So here we due to arching, I think I've already explained what arching is. The just a minute, free earth at a much lower depth. So because of the arching, these assumptions where we assume that the lateral earth pressure has a rectangular distribution, no sorry, as a triangular distribution. So this rho is trying to adjust for this because of the arching. The even the center of the center of mass, the lever arm that we assume is d over 3 is in fact so the lever arm is found to be, I think, shorter. So for that reason, the moments in reality are much lower because so this here, the phenomenal point of application of passive resistive force occurs at much shallower depth than the assumed value of d over 3, where d is the depth of penetration of the pile. Rho extended this worth to other soils. So computed by the free earth support for both moments in the pile, and the tension in the tie can be realistically reduced. The method involves the use of two coefficients Rd and Rb, and worked examples illustrating the use of the method have been prepared by that reference, Harden 1974. More recently, numerical studies performed by Potts and Forey have confirmed Rowe's finding for normally consolidated clays. However, their studies showed that Rowe's results do not stand for over-consolidated clays, and they have produced separate design charts for this. So, these are just some information to show you that actually this the point this guy is raising is this. We've said that we always take triangular distribution for the pressure distribution diagram, but in fact, like I've said, due to arching, we have some critical depth, z critical, which from where the uh, the overburden is constant, so that is the issue is raising. But also, so his results are only partially valid, according to some other researchers who found that for certain over-consolidated clays, we already talked about that, the results are not valid. So this is just some healthy discussion of how to apply this and what we calculate in theory, and when you go to the field, you find some differences, and so some healthy introspection to see that to check that we really can actually find exactly what is happening in the field. Which of these methods is the most representative when it comes to the design behavior in uh, in reality. So there's another example there. If an anchor is placed 1 meter below the ground level behind the sheet pile wall described in example 2, calculate the minimum depth of embedment to provide stability using these two methods. So the examples, the CP BS8002 and CP2 method. So in example 2, yeah, should be so familiar now, this one. Yeah. So this is the example which we have studied exhaustively, I believe. So let's see the how to tackle this. So So the BS8002 method, as before, we apply a surcharge of 10 kilonewton per meter squared and allow for future unplanned excavation of 0.5 in front of the wall, as shown in the figure 10a. The pressure distribution is then shown. So here we use the simplified version, and so the forces are so the only difference here now, these are the forces are still the same as what we have done before. So the passive side, this is the contribution due to the passive I mean the earth, and this is the contribution, of course, due to the surcharge. So then so PA1, PA2, so this due to the earth, that's due to the surcharge. So the only difference is the lever arm, because we offset it by 1 meter. In this method, uh, yeah, we place an anchor 1 meter. So what happens with that is you take moments at the anchor, all right? So so that's why you see the lever arm and subtract 1. Um, so, and then of course, if we took moments at the bottom, then the that was 5 plus d naught, or d over 3. But you can see we are taking moments here. So from this end, the distance is 2/3. So this is why 2/3 arm is 2/3, of course, minus 1. And you can do this manipulation. So for the moment as well, the force here is this. The lever arm is 2 over 3d plus 4, because on the passive side, I think this is should be okay. Let me try to make it. So here, you know that this is Kp. In the, you should know that Kp times gamma times h. Also know that in the gross method, this one is divided by 2, but this is not okay. I'm reminding you here, this one. So in this CP2 method, for the passive part, you have to reduce this value by half. Okay. Yeah. So here, so this is Kp. The lever arm here is what? 2/3, uh, 2/3 of d plus 5 minus 1, which is 4. This should be easy to figure out. So that's what we're doing here, and you know how to figure this out. If you have a question, you can stop me. Again, the ratio of the passive and active have to be, so this is the passive, this is the active, and value, the factor should be 1. The same, more or less the same what we did before. And by trial and error, you find the embedment length as 3.4. So note that in the previous cases, the embedment length was 6, around 6, 7, between 6 to 7. Actually, if you multiply by 1.2, it's actually up to around 9. But you can see now the embedment length has reduced to significantly to 3.4. So this is the idea. If you provide an anchor, then the embedment length can substantially reduce. And the treatment of groundwater conditions. So in order to carry out the stability analysis of a retaining wall involving groundwater, it is necessary to know the values of the water pressure acting on both sides of the wall. If there is water level on one side, let's some correction there. If there is water level on only one side, so if there is water on both sides at the same elevation, then the earth pressure values, the lateral forces can cancel each other out. Yeah, so if there is a so if this is your wall, and then the elevation is the same, uh, the elevation is the same, that's the water elevation. You can see that these pressures are going to cancel out each other because they act in opposite direction if the elevation is the same. So that's the first idea. Then the pressure will balance out. Diagrams at the same elevation, the two water pressure diagram act equal and act equal, and they balance each other out. Some error. So they balance each other out since they act equal and opposite. Hence, apart from the fact that the soil below the water is submerged, no special treatment is necessary. With different water levels on both sides of the pile, seepage can occur. So we took the most simple case that we have the same water on the same side. However, if we have water on different sides and different elevations, of course water would tend to seep. The one with higher level, water would tend to seep to the the issue of diving head. There is a higher head here, so water would flow to the other side. So an approximate method. So with different water levels on each side of the pile, seepage can occur. An approximate method to allow for this is to assume that the difference in the hydrostatic pressure on each side of the pile and its base is distributed linearly around the length of the pile, that is within the water zone. So H plus 2D, uh, where H is the height of the pile above dredge level and O is the depth of the pile penetration. So uh, when we have different elevations, it is easy to assume that the okay, let's say this simply put. So simply put, the water will flow is assumed to flow from the higher side to the lower side until the pressure is the same. All right. So picture this: this will have some higher distribution because of the Z. So gamma water times Z water would be high. Here maybe it's relatively low. Okay. So would be high because of the height is high, but here gamma water and Z water would be low. So as water flows, because the water level is higher than that. So as water flows to this other side, this the water pressure here, of course, is going to reduce, and this one is going to increase until they reach a point that okay, this is a passive and active, until the water pressure in side passive is the same as the water pressure in the active side. That's the assumption, and we assume that the distribution is uh, is uh, is the same along the penetration depth. So we have an example to illustrate this. Maybe it will be more clear. It's clearer. So example, determine an approximation for the water pressure distribution uh, on each side of the sheet pile wall shown in figure 12a. figure 12a. So with the assumption that the hydrostatic pressure are linearly distributed around the length of the pile within the water zone, the formula for pore water pressure on both sides is shown. So this is an assumption. This formula comes from the assumption the pressure, of course, is gamma times h, but the h is what? The z of the water. So gamma water times the height plus the penetration depth. All right. And when water flows, this is the, so water, you can see water will flow here. Now this distance is twice the penetration depth, because water would, the sheet pile wall is impenetrable to water, so water will, so that distance is 2d. So now you can see that, so 2 gamma times the depth and twice that, of course, divide by h d. So you can try here, you see for yourself. There are 2 gamma water into h plus d times d over h plus 2d. So that would work out to be to what? 2 times 10, 8 plus 6 is 14, times 6 over 20. This one goes here 2 times, 2 cancels 2, 14 times 6 is 84. So that is the uniform pressure on all sides. So you can see it's a reason for this. Then now so it is assumed that these pressures cancel out each other. So you can see this is this is positive. I mean, this is going this way and this is going that way. So we assume that the overall effect is that these pressures cancel out each other. So then at the end of the pile, so throughout the length of the pile, these pressures cancel out each other. That means the pressure will rise, the water pressure will rise to the maximum here and then reduce to 0 at the end. This is the net pressure distribution. So based on similarity and congruency, the value of this part, you can, so this length we know is 14. So based on, you can, so if this is 84, you can find out what this is, and that turns out to be 48. So if that is 48, this force here act at 8 over 3, and this force also act here at 2 over 3 times 6. Yeah, so, and the rest of this you can find the area. So if you know this is 48, then you can find the area of that and also the area of that part. So this is the net pressure distribution. Okay. So finally we talk about the Blum's method. We already said that you can have an anchor and but you need to know the forces in the anchor. Now this is somehow, you remember someone asked yesterday how to deal with if there were waves. So this is how to deal with the horizontal forces. We touch on this a little bit here, but you can see the pressure distribution here is quite complicated, and here. So here we say that the tensile force, not the anchor force would be the passive force minus the PP. But if we only knew this distribution, right? So for simplicity, sometimes we can assume that this is linear, but you can see the assumed pressure distribution from the actual pressure distribution is different. So Blum gave some method. I have to warn you, it's a little complicated uh, because I told you, for if we remove the anchor and you just want to find the penetration depth, you can see we end up with a cubic equation. But now if you add the issue of tens at an anchor force, then it's going to be a little, not impossible, but complex. So hopefully you follow. This is what the syllabus requires. I showed you yesterday. We need to talk about Blum, Blum force. So this is the last part. I'm hopefully going to make it very simple for you. So an alternative to the free earth support method, I think we already talked about this, and one that is more popular in Europe than in the US is the fixed earth support method, which we already also talked about. So this actually the fixed earth method is the Blum's method. To illustrate the concept, we present a simple example. So this was developed by Dr. Blum, Herman Blum. So this is a fixed earth method actually. The Here, this one. So because the syllabus says explicitly that you have to know how to calculate the anchor forces. Okay, so I'm going to now, this section is to show you how you can use that to determine the anchor forces. It's complicated. I'm just going to show you the expressions. Hopefully you can solve, but mostly by a computer. So consider an anchored sheet pile wall with a single support, uniform granular soil, and no water as shown. So here we even assume there's no water in an effort actually to make it even simpler. So let us assume the toe of the sheet is fixed, and for structural purposes, this is Blum's first condition, and this sets Blum's method apart from free earth method. If we neglect the anchor, the system will be simple. Yeah, cantilever with two distributed forces with active pressure. So I show you the diagram first. So here, this is the same thing we have been talking about, in fact, but in this case, we need to find the anchor force. All right. So the anchor force, if we ignore the anchor force, then these are just passive and active, uh, and the thing reduces to a cantilever, which you can solve like we have done before. So in that case, the passive force is the Ka. Of course, we are assuming the passive is negative, so the Ka times gamma times x. We remember here we are using different notations, but this is nothing other than gamma h, because you know the passive force force is Ka gamma h. That's all. That's what we're doing here. The passive force, the active force, because uh, so this is x, but the active force, the not the active force, the passive force So if this is H, no, if this is X, and this is H, then the active force is Kp gamma X minus H. So nothing there that is difficult. So X is the distance from the top of the sheet pile wall, the moment at any. So if you add the issue of the moment, then you just take this and divide by multiply by x3, and the same here, x minus x h over 3 to get the moment. So this is if we ignore the anchor force. So you can see, of course, in this case, x, the value of x is greater than h. Heck, yeah, of course. So now let us add a simple support at the point of the support. So we assume the this is simply supported there, and we now treat the the sheet pile wall as a beam. Then we take moments at, we include the moment t. So the moment due to this force at any point in the beam, so x is measured from here. So, and okay, x, so this is x. So any point in the beam, sorry, so x, so x is measured from here, so the moment due to that force is basically the tensile force into x minus you can see that, so as we have seen here, and of course here we are saying x is greater than ph. All right. So with the addition of the support, the system is statically indeterminate. At the moment equations, however, can be solved if we treat each of these three forces acting on the beam, active pressure, so three forces, active pressure, passive pressure, and the support or the anchor force separately, and then sum the reflecting deflections they produce at the support. We will use a dummy unit load method. This is the virtual work, you remember unit load. We will use a dummy unit load method to determine these deflections. This method states the deflection at any point can be determined by the equation. So this one is assumed that you have already done this virtual work method in structures. I won't get into the details. If the deflection, so these are the so this is the method, in fact. So this is the moment due to the dummy or the unit load. The moment due to the actual moment. E is the modulus of elasticity of the material. I is the moment of inertia of the sheeting or the sheet pile wall. For active pressures and the anchor force, one must integrate the support from x equals gamma h to the end beam. So x equals h plus 3. So we are just explaining what you must do here. You integrate from 0 to hd. For the passive, one must integrate from, so for the passive, so for the active, you integrate from 0 to h plus d. For the passive, you integrate from 0 to x equal to h, that's it, to the end of the beam. If we integrate the deflection of the anchor caused by each of these forces, sum the three resultant deflections, set them equal to 0, and solve for the anchor force we have. So we've tried to make it simple for you But you see now, even the simplest form, you can see the equation, the way the equation is. So let me try to explain simply. We treat each the effect of each of these pressures on the support here. So we treat them independently. We find the deflection due to the earth pressure at this point, the deflection due to the earth pressure, this is the deflection due to the active earth pressure at this point, the deflection due to the passive earth pressure at this point, and the deflection of the anchor force at that point. So we have three forces. Each of these have their associated effects. Now, for equilibrium, all those must sum to zero, so that's the point. And of course, in doing that, we use the virtual work. So this is the equation that can be used to calculate the anchor force. This is what the Blum said. We now note that we still have two unknowns, the anchor force T and the depth of penetration D. It is important this point that we introduce Blum's other condition. The moments about the toe equals zero. So the moment, the same thing we've been doing before, the moment at the toe is at the bottom, zero. Even though the toe is fixed, there is a reaction in the toe which represents the residual of the net force in the wall. It is generally counted for in design by increasing the penetration D of the wall beyond the excavation line by 20%. So again here, the D that you will get eventually you have to increase by 20%. People who are getting tired, don't worry, I'm almost finishing. The moments at the end can be obtained by substituting x equals hd in equation 3, 4, and 5. So in these equations, so we substitute here x equals h plus d in these equations 3, 4, and 5. If we do that, and of course sum the moments summed at this end, at the toe, all right. This is, I think this one now you should you know, because we have done this several times. So when you do that, if we then sum the moments, set the summation to zero, and as a result solve for them for the anchor force we obtain. So we have this equation, this is number 9, and equation, no, I think this numbering is wrong. We have equation 8, I believe, so this should be equation 8. So we have equation 8 and equation 7. Those equations are in terms of D and in terms of T, two unknowns and two equations from which we can solve. Of course, we have to make this note that you can see obviously the nature of the equations. I warned you yesterday that if calculating the penetration depth, even the simplest of form, we end up with a 3-order cubic equation. So you can see now when we add the tension, of course it's still 3-order, but you have to do some math. So this is better solved by numerical method. All right. Of course, you're expected in this class to know the theory of, or just have an idea of of what Blum's method is about. So obviously we can solve this equation and the previous one together and determine result of T and D. However, from a practical standpoint, only numerical solution is possible. If we add the water table, the complexity increases. So Blum's assumption of fixed end has been widely criticized, especially in the US, but it should be kept in mind that Blum's assumption is more of a design objective than an assumption of actual conditions. If the sheet pile to be lengthened, the maximum moment, which can also be obtained from the above equations, would be lowered with the increased penetration of the sheet pile. A longer sheet would also be more resistant to overturning failure. This concept, although applied first to steel sheeting, has potential with non-metallic sections where maximum allowable moments tend to be lower. So this is just to demonstrate the fact that there's the assumption he made is a little unreasonable. You can see people have criticized it, but you can see what is explained there below, that still we end up with lower. If we use this method, we actually end up with lower moments and safe design. So this assumption is basically based on a design objective rather than what happens in reality. And also at the end of it, despite its limitations, we end up with a safe design, and that is the in fact the objective of what we are doing. So because of the complexity, you can see those nature of equations, we are forced to make certain assumptions, which of course will give us a reasonable solution, which is safe, or which edges on the safe side. Of course, if you check the nature of the equation, so we need to find a way to simplify, to make it simple in a way that we can solve and end up with a safe design either way. So this is we finish this part. If there is a question, you can shoot. Be waterproof. The joint